Hello, this is the fifth video of the Algorithm 3 series on further algorithms and efficiency for OCR Discrete Further Mathematics. And this video will look at more packing algorithms, specifically for knapsack problems. The knapsack problem has been studied for more than a century, with early work dating back as far as 1897. It concerns the common problem of packing the most valuable or useful items without overloading the luggage. So it's a problem in combinatorial optimization. Given a set of items, each with a weight and a value or profit, determine the number of each item to include in a collection so that the total weight is less than or equal to a given limit, and the total value or profit is as large as possible. A large variety of resource allocation problems can be cast in the framework of a knapsack problem, with the capacity of a knapsack as the available amount of a resource and item types as activities to which this resource may be allocated. For example, an advertising budget for promotions of individual products, or student allocating effort to the range of topics or subjects prior to exams. If the problem involves a small number of items, we might use trial and error to find the optimal solution, but for a larger number of items, we need a systematic method to save having to check every possible combination. Very simple problems can be solved by using a common sense approach. So for example, if I'm trying to decide what gifts I should carry in my hand luggage, given that there is space for all of them but a weight restriction of 8 kilograms, I might choose to take something that has value 20 and value 5, so in other words £25 worth of gifts within that 8 kilogram restriction, or I could add the value of 15 to the value of 4, again within that 8 kilogram restriction, and only take £19 worth of gifts. The branch and bound technique is one possible systematic approach for these knapsack problems. Let's look at this example here, where a student wishes to take a number of optional items on a walking expedition of weights and values given in the table. Some of you may have been on walking trips as part of the Duke of Edinburgh's award scheme. The value scores are estimated by how useful or vital the item is thought to be. And note that although we're talking at about a maximum of 20 kilograms being carried, 5 kilograms of that is water and other mandatory items, leaving a limit of 15 kilograms. First, we need to calculate the value per kilogram. So, for example, with A, we would say 3 divided by 4, giving us 0.75. For B, we would get 0.63. For C, 0.8. For D, 0.67, rounding up to 2 decimal places, and for E, 0.71. We thus reorder by value per unit weight. We will now write what we call solution vectors, which are written in terms of zeros and ones. So for example, the solution vector with all zeros means we have packed none of the items, whereas if we had a solution vector of this form, we would have packed items A and B from this reordered table. So the branch and bound method means we start off by assuming that we're not going to take anything, and then consider taking either C or A or E or D or B. We use the reordered table to write in the values and weight by each of these branches. Notice that this red square means we will not be expanding that branch. Either because we can only add new items that occur after the current ones to the right, and B happens to be the most right hand value in the table, or because we cannot add any more items because we'd be over that weight limit of 15 kilograms. In that top expanded branch, the weight of C and A combined is 9 kilograms, so we can potentially add up to another 6 kilograms. And we could expand again to being 1, 1, 0, 1, 0, which would give us a weight of 15 and a value of 11. You'll note that those other branches all have red squares. In this first instance, we have a weight of 12 and a value of 9. So we'd only be able to add 3 more kilograms, and none of the items weigh 3 kilograms or less. Hence the red square. Similarly, for a weight of 11 and a value of 8. And then the red square is on this last branch here because we've already added B and there's no other values in the table to the right of B. Moving down then, we can consider 0, 1, 1, 0, 0, or in other words A and E being packed, and this would give us a weight of 11 and a value of 8. Having added E, we cannot add D or B, would take us over weight, so that would get a square. If we look at 0, 1, 0, 1, 0, so in other words A and D, we would have a weight of 10 and a value of 7. The only item we could now add would be B, and that would take us over weight, so that also gets a square. We could consider 0, 1, and then 0, 0, 1, in other words A and B, giving us a weight of 12 and a value of 8. Considering this branch, where we've started by loading E, we can look at these options, which would be a weight of 12, a value of 9, and a weight of 15 and a value of 10, and both of those will get squares. And then this would branch, we could look at adding B, where we would have a weight of 14 and a value of 9. Remember, we want the highest value within the weight limit, and looking down through that list, we would identify that packing C and A and D would bring us in exactly on the weight limit of 15 kilograms, and with a value of 11. So to summarize the branch and bound method, step 1, we would sort items in decreasing order of value per unit of weight. And step 2, we use the solution vectors with xi equals 0 if an item is not packed, and xi equals 1 if it is packed. And then the branching method, starting at the null solution when we pack nothing, and considering the combination of each item in turn. We repeat this for any branches that are not blocked by either the weight limit given, or by the fact that we can only add ones to the right of the last one in the vector. Finally, we compare the squared branches with weight less than or equal to the limit given, and then find the one with the highest value. We then stop. This is the final video of the Algorithm 3 series.